Yeah, it's great to be here. I want to thank the organizers, Michelle, Daniel, and the team at Saclay for inviting me. I think this is a really well-organized conference. I've been learning a lot from it, and it's a pleasure to be back in Paris, where I spent, I guess, what is now known as a gap year after college before I decided to pursue my PhD research. And so it's great to be back. Just this title, I decided to put my own title to go with Neutrinos for Peace. I think this may be a term of Michel's invention. It's a good one, perfectly adequate, but just one of the problems is if you tried to use this in the United States, you wouldn't get any funding because it's not a better neutrinos for defense would be more appropriate. But so a more anodyne term, applied antineutrino physics, is what we've come to define this area where the emphasis is on reactor antineutrinos. And just foreshadowing for this talk is what I mean, and then also just kind of a look back at Reinus's thoughts on his life. He says this, I don't say that the neutrino is going to be a practical thing, but it's been this time-honored pattern that science leads, technology comes along, put together, they make an enormous difference in how we live. So, you know, this was said in 1997. I've had this quote up before. The only thing that gave me pause at this conference was Cecilia's comment that sometime around 95, he kind of may not have been completely as lucid as he was in his earlier years. So I hope this comment is a moment of lucidity that defines the potential of neutrinos as a practical thing. So what was he at least potentially talking about? Near-field reactor monitoring, I'm just going to define that term here. What it means is to monitor the operational status, the power, the thermal power, and the fuel consumption, the composition, whether there's plutonium or uranium in the core. And then the near part means basically less than, loosely speaking, a kilometer, but typically 10 to 100 meters, and you know, you're having access granted by the operators. I'll spare you the details of the fact that there's an agency, the International Atomic Energy Agency, whose role it is to essentially pursue this effort of tracking fissile inventories worldwide. But it's an important activity that can be improved upon what is currently being done. Another feature of these, this sort of circumstances, you have relatively high statistics for a neutrino experiment. So instead of, you know, sort of one event per year, in this case, you're going to get a few thousand events per day per ton. That's more than adequate to populate a spectrum, which you can extract in inverse beta decay detectors. And then the reactor powers that we're talking about, anywhere above, you know, something like 20 megawatts thermal, below that it becomes challenging. The main focus, just because most of the reactors that are under safeguards or under monitoring in the world are about a gigawatt thermal or above. And then if you look at this plot here, what I want to do is just point to its value from the application standpoint. Of course, naturally, one is drawn to this plot. You saw this earlier today in Thierry's presentation. The number of observed versus expected events in a reactor experiment as a function of distance from the core. What's interesting about all these, which from a basic physics standpoint are a null result, is that they all give us technologies that could be appropriated and made use of, even if their initial physics goals didn't come to fruition. And so one of the nice things and sort of simple things about this, I won't call it a history, but a remembrance, is that it's very easy to trace its origins. There's this remarkable conference, Neutrino 77 in Baxon, perhaps somebody here was there, in which it was really Michelian as the first recorded or published presentation on this topic. And he basically summarizes, all the ideas that are then going to play out over the next 2 decades, as I'll show you in a moment. First of all, just remotely, by which he means sort of tens of meters away, understanding the properties of reactors through their neutrino radiations. You can basically look at the power. You can look at the dynamics of the fissing isotopes. By this, he means the quantities of 235 and 239 plutonium in the core. And then another thing I just thought was kind of amusing at this conference, it was a basic physics conference. All the details, which indeed are, to some degree my preoccupation in my day job, is what you actually do with these detectors. Not really relevant for that conference. It was more about basic physics, not about the applications. And so in the same spirit here, this is about applied antineutrino physics, but I'm not going to talk to you that much about the regimes that employ these detectors, but more about the detectors themselves. Okay, so a quick kind of somewhat arbitrary, not quite random whistle-stop tour through the R&D that has led to the present day of what I consider to be a fairly mature field. So as I said, it all started with the idea being recorded at this conference in 1977. And then there's something it's maybe appropriate to call the Rovno era. So Rovno is a reactor in the Ukraine at which a number of really remarkable and good experiments were done. It's one of the experiments that you saw on that plot of short baseline experiments. And really all the basic ideas of reactor monitoring were explored during the Rovno era. I'll show you some of those in a moment. Then we, much later, this is one of the good things, you know, had I had knowledge of what was going on here, we might not have pursued this effort at San Onofre, which is what SONG stands for, the San Onofre Nuclear Generating Station. Really, all we did pretty much is essentially rediscover or re-explore these ideas. We did make some minor simplifications, and we attracted the attention of the International Atomic Energy Agency and sort of made some progress that way. And then just as a sort of kind of personal point of how this got going, so, you know, I was a postdoc at the time and sort of did not know either the San Onofre site or where to get the materials that it would take to build a detector. And the people at Caltech who came off the Palo Verde experiment had leftover Palo Verde scintillator, which they generously donated to me. And so that was how the effort got started. The other thing that they did, I think it may have been Thierry or somebody who talked earlier about the difficulty of getting into the Diablo Canyon site in California and the resistance that that site felt towards having a neutrino detector there. Here it was because we had a foot in the door with the fact that the folks at Caltech already knew them. They spoke to the president of the, or you know, the director of the reactor. And basically, I think these are very hierarchical institutions. So once the director agrees, then pretty much everybody else follows suit. So we had a pretty easy time of getting our detector into that site. Okay, what followed was this, I think, to some degrees inspired, or anyway, was alongside a number of sort of theoretical analyses of spectra, but also case studies looking at these detectors deployed against particular reactor types, particular configurations. Patrick Huber was one of the strong early advocates of that, and others joined him in that effort. And then, you know, sometime roughly a little bit in the middle or towards the end of the effort at SONGS, which was ongoing for just about a decade, there was what you might call a Cambrian explosion, or at least a large number of detectors that were built in order to optimize this idea of monitoring reactors better and better. What SONGS did was relatively simple, and I think the thing to the sort of dichotomy that one wants to be aware of here is that there's a trade-off between the ideal detector from a physics standpoint and the ideal detector from a standpoint of deployability. So you want something that's easy for somebody who doesn't have a PhD to operate and to use for a long time, but you also want something that works effectively as a neutrino detector, and those are not necessarily the same detector. So a lot of this effort was geared towards that optimization, and this was in a somewhat, maybe this was before the sort of attention had been attracted to the reactor neutrino anomaly, but essentially what happened was that a lot of the sort of ideas that then went into the short baseline reactor experiments came out of this applied neutrino physics effort around the world. So another thing that went on was starting, and again, this is a place where you can give John Learned a lot of credit. He was the first to sort of do a workshop dedicated to neutrinos and arms control, University of Hawaii. Since then, there's been pretty much an unbroken series of applied anti-neutrino physics workshops around the world, which is sort of keeps the community alive. And another thing that happened, which partially due to us, but also I think the people at Rovno had something to do with it, was these IAEA workshops. So the IAEA you can think of as the customer, the person that you would, the group that you would ultimately want to make use of this technology. And I put these as footballs because these were sort of, fairly political workshops in which you're bringing to the IAEA a technology that they might not want to hear about. It's potentially an improvement on what they do, but it's also something that's a disruptive technology that requires them to reorganize their activities and do something that they're not used to. And so it's not easy to get the IAEA to embrace a new technology. Just to see if this slide catches up here. Yeah, just to go back for a moment and look at what was going on at Rovno. here's sort of the first experiment that was dedicated to just doing reactor diagnostics. And this is in some ways the ideal experiment for this purpose. There's overburden, which is given by the reactor core itself that you see here and the earth that surrounds it. The detector is relatively small, so 500 liters of liquid scintillator. One can afford that because you're so close to the core, you get high statistics. Not a terribly large number of photomultiplier tubes. And you're fairly close to the core, but you're actually in a fairly low radiation environment, not only protected from muons by the overburden, but also just shielding from the reactor core itself. And so the detector can operate with pretty good signal to background. I'll show you that here. So this is just sort of the first thing you would think to do is simply monitor the reactor's power. It's kind of the easiest or most straightforward thing to do. You just see the on and off cycle of the power as it goes through its various gyrations. This is 2 months of data in one of the early Rovno experiments. And then here's the interesting thing that I would normally dwell more time on just as to how the physics works. This is a variation over the course of the cycle. So you're looking at about 600 days here. In the anti-neutrino rate, note this is zero suppressed, so this is about a 10 or 15% effect on the rate. And that's just coming because plutonium is growing into the core, uranium is burning out, and each of them generates a different number of antineutrinos above the IBD threshold. And as a result, there's this gradual decrement in the rate, which you can essentially use as a clock to define how much plutonium or uranium there is in the core, if you have a thermal power measurement. So we did this. This is data taken at San Onofre. This is the detector here. Rovno also did this. I just didn't have a good plot of it, so I showed our own work. Okay, and here's another really important thing that's also remarkable that was done by the Rovno group. So the first people to pursue this is actually measuring the spectrum of antineutrinos that are coming out of the core and looking at the ratio of that spectrum at the beginning of cycle compared to the end of cycle. If you have this spectral information, basically you no longer need power levels or other extraneous information that would otherwise be provided by the operator. So instead you can just rely on the antineutrino spectrum, and it's kind of rocking as it moves through the cycle to infer the plutonium content of the core. And so this plot is just showing that spectrum at the beginning and end of reactor cycle and showing that there's a hardening because uranium tends to harden the spectrum and plutonium softens it, and this ratio shows that evolution. And then, somewhat later, if you essentially take this detector and modernize it somewhat, so you make it about 5 tons, you improve the energy resolution, it seems that if you deal with relatively small reactors, so this, remember, was about 10 times as energetic or so, or 20 times as energetic, but even for small reactors, because the ratio of the change that you're looking for to the total amount of plutonium in the core is larger, it's easy to see relatively small changes in plutonium. This 7 kilogram number is significant because there's a concept in the monitoring world of a significant quantity, meaning the amount of plutonium it would take to make a weapon, and that weapon is nominally deemed to be 8 kilograms, and so it's good that with 5 sigma sensitivity you can use these spectra to tease out that information. Okay, and then just the last word on what I might call the near field is one thing that's exciting that's happened, again, is this nice sort of crosstalk or interplay between fundamental and applied physics. Prospect is something, a US experiment, a short baseline reactor oscillation experiment in which it was sought to measure a spectrum. And what's interesting about this is you've seen these curves for, as you know, going on 30 or 40 years. This was done at Rovno, not so different. The difference is it's above ground. So that overburden of 10 or 20 or 30 meters that was relied on by the old experiments is gone. This is maybe a meter or so of overburden, which is just the building in which the detector is housed. And even in that difficult background environment, they're able to pull, this is only 24 hours of data, it's a very recent result shown at Neutrino 2018. They can see the neutrino spectrum with some imperfections in it, but nonetheless it's remarkable to be able to reconstruct the spectrum at the surface of the Earth. So this next generation of detectors, Prospect, Newlat, Chandler, et cetera, what we hope will happen is that they will end up optimizing and simplifying the ability to sort of deploy these detectors without having to rely on overburden. So that's the last thing I'll say about the near field. And then I just want to see if I can get that back. Just wanted to draw one slide. I was able to take a photograph from Gary Feldman's very nice talk yesterday, and it says here that And this would seem to be true if you think about basic physics. Studying oscillations is the only possible reason to put your detector hundreds of kilometers from a target. And I just want to say, well, there is one other possible reason, and that reason is the far field. So this is, Reina said, a practical thing. This is maybe at this point a somewhat less practical thing, but we're working to make it a reality. So in the far field, what we're talking about is looking at, basically hundreds of kilometers out to an ultimate limit that might not be any more than 1,000 kilometers with varying degrees of access. Here it is more like a rare event search. You're looking at a few events per week or month, or per explosion if you try to look for the explosive yield of a sort of CTBT, comprehensive test ban treaty context. And then the reactor powers that you care about, the ones that are sort of not already known around the world is maybe about 50 megawatts thermal. What kind of technology could you conceivably use to do this? Well, so CAMLand, of course, is the first thing that would spring to mind. I'll show you why in a moment. Super K could also be interesting, but there's a little wrinkle in that we think is now solved. And basically other large detectors would have to be used, and these have been taken as examples by a number of authors, as I'll show you here. So this is kind of the timeline for maybe not as active a field, but certainly a lot of interesting work has gone on. I'll just show you the relevant experiments and analyses. So the first is one of the early papers that I did, at least that I could find in the literature, is I proposed gadolinium-doped water to do essentially CTBT monitoring. This would require something like a 300,000-ton detector, but it would only get you, I forget, something like 60 or 100 kilometers away from a relatively large explosion. And so the conclusion was that compared to the existing capabilities within CTBT, probably you wouldn't want to pay what we estimated would be a very large price tag to build such a detector. Now that was a sort of naive and early analysis, but it was sort of a shot off the bow. As he is wont to do, John Learned sort of took it one step further, not in the context of explosion monitoring, but looking for hidden nuclear reactors. And here he just proposed, he sort of opened up the imagination and said, if you had a gigaton array, if you had these monitoring detectors spread about the world, what could you discover? And he did some sort of basic analyses of that, and that was one of the early ideas for just doing remote reactor monitoring. And then this was kind of an important element, not that it had anything to do with applications per se, but it just clearly showed you that you could see reactors from far away with about a kiloton of scintillator. I'll show you that plot in a moment. Then came some more interesting work on sort of more detailed analysis of how you would go about doing far-field monitoring. So not that many publications. I may be missing a few. I do, though, want to mention this one, not just because I'm here in France with Thierry nearby, but because this is important because it was a really nice and detailed treatment of both reactor and non-reactor backgrounds. It was done by extrapolating from CAMLand and Borexino. The earlier experiments had been, papers had been somewhat more cavalier in those treatments. And this was, I think, one of the first sort of careful treatments of this problem. And then there was this interesting device called EGADS. This was a sort of 200-ton gadolinium-doped water engineering demonstrator. And in a moment, I'll give you the story of why that's important. I know I only have a few minutes left. Also, just people have been studying and doing sort of reference maps of these are all the reactor antineutrinos all around the world, and this is estimates of the antineutrino output published in about 2015. And then, let's see if my animations will work. Hold on. There's just this improvement on this original 01 result, which actually shows you can do a little bit better if you seismically cue the antineutrino detector. You need, therefore, less statistics and can get by with a smaller detector. And then maybe most importantly for the future, and this is what I'll talk about in the next 2 minutes or so, Watchman. This is a new initiative, US-UK proposal now funded to build about a kiloton or so of gadolinium-doped water, exclusively devoted to this question of reactor monitoring. And then Super K is now happily being upgraded to having gadolinium-doped water, and I'll show you why that's happening on the next few slides. So first of all, just the idea, as you sort of know this in your unconscious, but to articulate it, that reactors can be remotely monitored. This is South Korean reactors constitute a few percent of the signal in CAMLand. There was the unfortunate experiments of all the reactors in Japan being turned off, and yet the signal persisted. So there's no doubt, of course, that one can see reactor antineutrinos, very low energy antineutrinos, even at long distances. The issue with this is that we already know where all these reactors are, so it's not terrifically interesting to find out where they are again with the technology. And then the other thing is, if you think about the scale that you need, is something like 100 kiloton to a megaton. 1,000 tons of scintillator is hard to scale to that level, so one is naturally led to the alternative of water. If you were to try to just take super K and appropriate it for this purpose, you would be swamped by all the backgrounds from elastic scatters. You have neutrino hits electron, creates a scatter. But that looks identical to inverse beta decay on proton unless you see that neutron. So you really have low efficiency for that neutron in super K. The way to resolve that, which we and the super K collaboration did around 2009, was just to show that if you add gadolinium to the water, then all of a sudden you pick out with great efficiency that neutron signal. Then you can give a very clear and robust tag for those inverse beta events and pick them out of an otherwise difficult background. Okay, so that brings us to what we're doing with Watchmen. This is now, it's not strictly speaking history, but it is the near future. This will start really in October of this year. We'll begin excavation of this site. I won't dwell on this, but just to say that this is happening 25 kilometers away from, what's interesting is there are two cores, so you have sort of the difficulty and the advantage from a non-proliferation standpoint of watching those two cores turn on and off and making sure that you can track that. And then compared to other activities worldwide, we're sort of situated between this experiment, which was sort of an engineering demonstration, not large enough to see reactor antineutrinos, and then the whole interesting and robust program in Japan of super K gadolinium and hyper K, which will go from 50,000 on up to maybe 500,000 tons. Not clear if this would be gadolinium doped water or not. And this is, of course, is devoted to basic physics, whereas this is purely, at least for the moment, a exercise in non-proliferation. So just the second to the last slide is that I think it's fair to say that this is really a mature technology at this point. We now are approaching the point that we have essentially easily deployable, or soon will have such detectors which can be driven on a truck to a reactor, left there for a period of time, and monitor operations. That'll be an important breakthrough that the IAEA would like to know about. And then this more speculative but still possible idea of far field detection at sort of hundreds of kilometers. Of course, CAMLAND has already demonstrated it, but Super K and Watchmen will show that the water-based technology can do the same thing. And just, sort of a near final comment that in all cases, the technology, there's a very natural overlap with what's going on in particle physics. The detectors are quite similar in many respects, and one should take advantage of that. And then nearly last, I want to say just there's so many ideas here that I didn't talk about. One of the most interesting is coherent scatter, which might allow you to shrink the size of the detector down, as well as other sort of technology advantages that to come. And then just to wrap things up, I just want to say, I talked about the origin story of Rovno, which is pretty clearly the place where many of these ideas got started. But you could even go further back, if I can get my computer to obey. And just look at Molière in 1670, and that's where he says, wow, I'm so grateful I've been speaking prose without knowing anything about it for my whole life. I'm much obliged you have taught me that. What I mean by that is that the particle physics community has been building these detectors for some time, and they can be used for this very prosaic purpose of monitoring reactors and discovering them. And it's kind of like you're doing it without thinking about it. You might as well be aware that you are doing it and take advantage of it. So let me stop there. Thank you.
Thank you. Questions?
So if you would put gadolinium in hyper K, at what distance could that detector see reactor activities usefully, and in particular distinguish individual reactor activities? There are many reactors and other sources. What are the possible distances in kilometers in practice, you think?
Yeah, it's basically, so with something like hyper K, if I assume it's 500,000 tons of water, just for sake of argument, doped with gadolinium, it's probably kind of 100 kilometers or so from a small 50 megawatt reactor with no other large reactors nearby. And so that gives you an idea of the scale. So I would say if you were to build it in Japan, that would not be a good place because there's so many reactors there. But other places in the world, for example, certain, well, I'd rather not go into locations, but there are places where it would be interesting to deploy such a detector.
Art?
If you're looking for the extraction of 7 kilograms of plutonium, are there ways of replacing what's extracted with uranium that you can detect if you don't have a spectrum?
Yes, there are. I may have a backup slide on that. Let me see. This gives you not 7 kilograms, but this is still a need within the non-proliferation community, and that is there's this sort of hangover from the Cold War of, as you may know, enormous amounts of plutonium that were generated for weapons purposes and no longer of use. That's about 50 tons in both Russia and the United States. A proposal to get rid of that is to irradiate it in reactors, so you have more plutonium than you would normally have in a reactor. And what you're seeing here are relative rates and different evolutions according to which type of core you have. MOX refers to mixed oxide fuel. It's a mix of plutonium and uranium. LEU is kind of the standard evolution that I showed you before. And what you can see is that it turns out if you do a statistical analysis on this, within a few sort of 100 days or so, you can distinguish between all these different families of curves and know how the reactor is evolving. You can't do it at the 7 kilogram level, but in the context that I just talked about of these 50 tons that you want to get rid of, you would easily be sufficiently sensitive.
Michel.
Yeah, Adam, you mentioned very briefly the coherent scattering, and I remember that in the first meetings that we had with IEA, people of the agency were very afraid of the size of the detector, especially because they have in mind super K, so they didn't see that we can do other things. But surprisingly, they were already aware about the possibility of coherent scattering. But at that time, we were reluctant to speak too much because it was not yet detected experimentally. So do you think that there is, we can think to promote a little bit more this coherent idea now?
Yes, although I think that would be a fine thing to do because coherent scatter has promise. I'll remark it has not yet been discovered at a reactor. It's been discovered with a spallation source, has about 10 times more energy. But even if you did discover it at a reactor, you still have the issue of shrinking it down so that it's competitive with the inverse beta detectors. And those detectors are basically a few cubic meters at this point. And so, and they're now spectrally resolving and above ground. And so one of the things that the IAEA was concerned about is having to disrupt the reactor operator by having to go into, say, the containment dome and put your detector there. If you can just drive a truck up, there's much more possibilities for deployment. So yeah, I'm super interested in pushing coherent scatter as a potential path, but I don't think it'll be the first thing to be adopted. Oh, if I may, I just wanted to revisit something that in Art's question. I want to make clear there's no spectrum involved there. The spectrum is integrated. It's just pure rate, and yet you can make this distinction.
It looks like you can get a spectrum with the detector you have on the left and the right.
Yes, that's right. So it was different. These are two different options. So this is what we said here is we deliberately wanted to not use a spectrum and see how well we could do because you can therefore make a simpler detector. So this refers to that trade-off I was talking about before. If you can afford to put in the number of phototubes that would be required to get this beautiful spectrum, which I think is kind of like a Dia-Bay or double show type resolution, then you can do quite well. And this is this 7 kilogram number I was referring to.
John.
So I just wanted to make another cultural point in relation to this conference, which was the way I got into this business and we in Hawaii got into it. We didn't know what Adam was doing, and they came around to see us looking for new ideas after 9/11. And they said, what can you do for your country? And I said, neutrinos, nothing. They're useless. And they said, well, you think about it for a while. So we started thinking about long-range neutrino detection. And so they gave us money with a wonderful, wonderful advice to say, don't think about how much it'll cost. Tell us what you could do, what we could do to monitor all the reactors in the world all of the time. So we had a wonderful time thinking about that. And it's, of course, totally impractical. One thing, however, that hasn't been mentioned at this meeting that I think will be important in this business in the future is what we call NUDAR, is that the observation of a spectrum from a single reactor, and of course Thierry and company have talked a little about this, but what people didn't realize is that with a relatively small number of neutrinos doing, you can think about it, the Fourier transform of 1 over the spectrum, or a correlation function swept across, it becomes something that we call like NUDAR, because you can get a range rather precisely from a single point out of a passive observation.
Right. I
And-
mean, John, if I may just comment
Yeah.
on your comment.
Yeah.
I brought back up this slide because we've had this discussion before, and that is true that if you can sufficiently populate the spectrum, you can get some idea of the sort of
Yes,
depth of the
yes.
interaction. But, you know, as I say, in this context, you're talking about events per week or month, not year, but probably a few events per week or month. So it takes time to build up a spectrum
Yes,
like
yes.
that. And that may make it difficult.
Yes.
You mentioned this very briefly in your talk, but then you didn't go into any detail. What is the current situation of the seismic compared with neutrino detection? What kind of ranges are you talking about, and what kind of signals or magnitudes can you detect?
Yeah, so
And are you allowed to talk
fundamentally
about
what
it?
it does is it takes kind of 10 or so events that we assumed in this 2001 paper down to maybe 2 or 3, or the statistical limit. And that means you can shrink your detector by that amount, which is obviously good. Because, you know, obviously the chance of there being a seismic event and a 2 neutrino burst when those neutrinos are quite robustly identified is very low. Yes, you know everything about the location from the seismic event, and then you can kind of infer things about fission yield or decoupling. So I'd encourage you to read this paper here, which actually I think was may have been their editor's suggestion last month or something. I'm co-author on it, and it suggests that you would do maybe a factor of 5 or 10 better than what we suggested in 2001. Not likely. I mean, I think our conclusion in that paper is that what you might do is if you're thinking about siting future large detectors for physics, you might think twice about where you would put that if you consider the benefit from a non-proliferation standpoint. So in other words, if you had 2 choices that were equally attractive and one of them had sort of more non-proliferation impact, you might think to do it that way.
Okay, I think we should close here. Thanks again.